Well, everybody, welcome into this video. In the last video, I left you off with this screen, and I did say I was going to go into the grid convergence index method for mesh independence in this next video, but it seemed to me a little bit unfair or maybe incomplete from my perspective to talk to you about possible ways that you could go back and look at and try to fix up or find out what was going on with, in our case, design points of angles of attack of 4, 5, and 6. If you do recall from the last video, we were getting an out of range value here at an angle of attack of 5, which was design point 4, um, where our trend seemed to be making sense. Everything was looking good. It was being validated by um, data that we had, experimental data in published documents. However, at the angle of attack of 5, we hit a dip. Our lift coefficients had dropped. Our drag coefficients themselves, our drag forces, went up significantly, just to come back into an apparent trend at an angle of attack of 6 degrees at design point 5. So I did leave the last video saying, check this, check that, maybe it was this, maybe it was that, and it just seems a little bit incomplete to leave you at that. Now, this is a major pitfall in CFD, and it's one that I fall into all the time. I know I'm not even worried about angles of attack of 5 degrees and 6 degrees. I'm not even worried about angles of attack of 3 degrees, possibly not 2 degrees, because I know I want to run my airfoil at 0 degrees. So the big question is, why am I bothering my head about trying to find out what's happening at setups that don't even register or will not even come to play whenever I set up my eventual larger build, my eventual larger CFD application. That's a problem. And you just go down into these rabbit holes and you keep digging. Two sides of that: you can just ignore it. You can say, right, look, I don't know what's going on there. That's for something else. Or what you can do is you can dig into it a little bit, seeking you at least find out what's coming, but what's happening, because this is going to happen again, and it might actually happen the next time that you are, within the range of angles of attack or the range of parameters or setup uh, that you do care about. So I don't feel awful bad about going into this just now. I do know it's creating another video. It's taking up time, this and that, but it is definitely worthwhile. So my suggestion on this is that we go back into Fluid and make a couple of the changes. I'll talk to you about why I made the changes that I have made. We'll rerun all of this again. I'll pause it, obviously, and when it has finished solving for all these design points, I'll start the video again, and we'll see what it looks like. So what we'll do, it would again, just what we are looking is going to be in around these larger angles of attack. So I'm going to come back on into the project here, and let's dip on into the solution. I'm going to pull my mug over to this side so I can access the navigation on the left hand side. And just starting up here. Right, so first thing I'm going to do is I'm going to ensure that I have given Fluent enough iterations to ensure that they've converged. Now, I think that I have. Okay, I don't think that I have currently set up a 600 iterations maximum iterations in this. I don't think I've ever gone as far as 600 iterations. But if I haven't, that's fine. I can put this up to a higher amount of iterations. There you are, 600. I can bang that on up till 1,000. If I don't need 1,000, I won't go to 1,000. Now, it'll stop iterating when I've hit all my convergence criteria. At the minute, my convergence criteria are obviously my residuals, which are my two momentum equations, continuity equations, the two turbulence equations, and then the two transition equations. What I'm going to do, and also the lift coefficient and the pressure coefficient also have to converge. So I have a problem because my lift coefficient, pressure coefficient at angle of attack of 5 have obviously converged. So the value that ANSYS has found thinks that, yeah, you've converged. So there could be a problem with how I'm converging. So if I go into my convergence conditions with respect to drag, and pressure. I'm ignoring 20 iterations, the first 20 iterations, which are fine. And I'm using 10 iterations. I need to stay below this value for 10. I'm going to scoot that on up till stay below for at least, I'll go for up as high as 40, and I'll tell you what, I'm going to go for 42 iterations. Why? I'm just going up in sixes these days. And for that matter, I'm going to drop that down to 18. By 18, any initialization that I would have done on all my cell centers prior to running the calculation should have, I'm using an upwind scheme, should have filtered their way downstream and threw me enough off a kilter not to have successive, or at least 42 successive iterations where I'd be below my convergence or my stop criterion here. And I'll check, maybe I'll drop that down to checking that again every 3, that's half a 6. Drag coefficient, pressure coefficient. What I'm going to do as well, just when I'm here, I'm going to delete these. What's going on? I saw that, just delete it, and I'll tell you why. I just thought of something else. I'm going to put in another report definition here. Put in a new report definition, an expression. And what I'm going to do is I'm going to encapsulate the two of them together in what's called an L over D. It's probably something I should have had in from the outset. So lift over drag. It's it's an interest of, it's a parameter of interest in a lot of airfoil applications where you don't specifically talk about lift force or lift coefficient and drag force or drag coefficient. You look at them as a ratio. So what we can do in this one is, as I said, what are we going to write? I have these in report definitions. I'm going to go to lift coefficient and divide that up by drag coefficient. So you can find it there, or you can write it. So curly brace drag hyphen coefficient. Curly brace, if it is right, it will go to bold green like that. You can do lift coefficient over drag coefficient, or force over drag force, doesn't really matter, so long as you don't mix your coefficient and your forces. So do not do lift coefficient over drag force or drag coefficient over lift force. Coefficient over coefficient or force over force. The lift is the one on the top, so L over D. I'm not going to worry about report filing, and I'm going to create an output parameter for this one. And hit OK. Now don't X out of that. Takes a wee bit of time for it to register, but give it the time to register and go out, or else it won't show up in your parameter table. Now what I'm going to do is come on into my convergence conditions, and I'm going to add one in, and instead of having converging on lift, and converging on drag independently, I'm going to converge with L over D, drag L over D, converge, that's L over D, stop criterion. Okay, let's make it a wee bit tighter for it to converge. Again, I'm going to ignore the first 18. I'm going to run at 24. Check every 3. Good enough. And let's just double check our residuals, which are here. So there's our continuity, our 2 momentum, K, or 2 an omega, 2 turbulence, and 2 transition equations, iterations, 1,000. Yeah, okay, grand. The residuals are always going to be checked as a convergence criteria. And now I'm also adding in L over D. I could put in pressure coefficient as well if I wanted to, and maybe I just will. Let's go for press coef. Coefficients are a good thing to use on convergence criteria, because coefficients obviously are created by inputting many variables or parameters, which means for their convergence, it means the inputted variables or parameters should have also converged. So there's pressure coefficient, and again, let's tighten it up. Again, we're going to ignore the first 18. Let's go for 24 on there. Now, I do think these have converged fairly well, so I don't think there's a major problem in that. Okay, so that's really all. They're the main suggestions that I would take in. A couple of other things to consider. I'll just bring them up now. In our models, of course, we're using the transition equations here. I do know in the Winslow paper, the single equation that the Spallart-Almaras model was used on that. So the results could be slightly different, but I do not know what his mesh was like, and I would I can't even recall now if his was done on a 3D or a 2D model. However, I'm going to stay with Transition SST. I do still think it's going to be a better model to use at that Reynolds number, um, with that flow. And as well as that, the methods, there's nothing really to change in the methods. Someone did send me a message and say, why not change it to simple or simple C? Yeah, obviously you can. Using simple C in this, it will work. It'll work fairly good on this, and it'll actually improve some of the stability at the very start. But the coupled method I still think is the best one to run with it. And then no one had mentioned anything here to do with the spatial discretization, which I was pretty shocked at. As usually some people come in with great ideas on this. The only thing I could have thought that we might have been able to do in this is going for, say, the likes of the greenhouse node base. That's the heaviest on computational effort to resolve this, which is to do with the convection terms, I believe. But you need a very structured mesh for that, which we do. But like changing things in here, I would really reserve that for three-dimensional analysis. And a lot of these, are fine on a very structured mesh. If I had an unstructured mesh, I would do different things. Maybe, especially when you're looking. Well, obviously these have to do with dealing with diffusion and convection and whatnot. The least square cell based is kind of it's a good, steady, dependable solver. These can be more accurate, I believe, and this here being the most accurate, most computational, expensive. But yeah, 3D, it's good enough when you do it in 3D. Look at these. Other than that, least squares is best. Second order is fine in that. There's nothing really else for these ones to go with. Linear is just not. You're gonna lose a lot, like, of diffused pressures between cell centers and them. It's an oversimplification. Presto, no, not so much. The second order is probably the best one. The momentum in here, what we could possibly do is go with a quick method in that, which I believe is a quadratic upstream interpolated convective, or for convective kinematics, maybe. If I recall correctly, I can't really remember. But again, looking into 3D could be a better one. Now you could run a quick one on this. You probably would get something a wee bit more accurate. But again, for a 2D, and when we haven't even done a mesh convergence study just yet, second order upwind is fine. Turbulent kinetic energy, yeah, there's very much same sort of ideas on them, and nothing else down here. Everything else is second order. For a 2D airfoil application, external flow application that has a good structured mesh, a second order approximation is about, is good. It's solid, it's reliable. So that's why we're going to run with that. Time stepping, yeah, we can change the time stepping, but we have 29 meters per second. We're just going to assume after initialization it's going to have 29 meters per second filtered out to some degree from an upwind scheme down. For upwind going back down, that's what upwind means. And it is steady. We have it in a steady state, so I wouldn't change that so much. It's fine. So there's nothing really else to change in here with respect to the methods that we're using, or anything to do with our pressure velocity or spatial discretization schemes. So that's what I propose we run with. I think our main difference is going to be made by the convergence criteria, that we are going to make sure that it is below our tolerance for a longer period of time, just to kind of, I suppose, mitigate the event where it dips down below and then it comes back up again, because it's just not fully resolved just yet. So yeah, that's what we're running with, and just want to make sure that our characteristic cell size, everything is good there. Yeah, because that was the last thing that we had changed. So there's nothing else that I would suggest we change on this. So what we'll do is let's leave this, exit, and of course we're gonna use these settings. for current and future calculations. Now I'm not running the calculation here. I can, but if I run the calculation here, it'll only run my current design point, which is design point 0, which is the 0 angle of attack. I'll then come back out into my table after I've ran that, and I'll see all these lightning bolts and every other design point, and I'll have to run them out here. And in fact, when I run them out here, I select to run them out here, it might even run design point 0 again. Now, one other thing that I am going to do this time is I'm going to retain data for design point 4, 5, and 6. Again, this is nothing to do with what I'm interested in for this project. And when I started a video 1, I did not intend to go into this. But yeah, there you go. It's fluid dynamics. I love it. And I just want to find out what's going on. So why did I retain the data here? Well, if I retain the data on that, I'll write the data that's been calculated at the design points into a file where I can right click onto that. I could set that as current. I can then go into Fluent and I could look at my contours, look at my velocities. If I have something out of range, I could potentially see something on a contour, for instance, the likes of a laminar separation bubble that has just appeared, which is at that angle of attack, which is saying, all right, yeah, now I get it. That's why the drag's gone way up. Or maybe there's been a laminar separation bubble developing at an angle of attack of 4, and when I put it at 5, it hasn't reattached. So there was laminar separation earlier that hasn't reattached. So can you really call it a bubble? Maybe not. But it is broken off the wing when I just put it up at 6 degrees or 5 degrees, and when it hasn't reattached again, it hasn't just caused a bump, but it's caused potentially a region there of minimal stall. But what it's done is, poof, I've just lost a wee bit of lift there, and my drag has come back because of that. Maybe, I don't know. And because I don't know, that's why I've hit retain to try to get an idea to know. Okay, so there we go. That's what we're going to do now. All right. So I'm going to right click into here. I don't even have to right click to update all design points. I do that up here. All right. So I'm going to click update all design points, and all this will get kicked off. There we go. Loading current solution. I'd say everything's hunky-dory, ready to rock and roll. So what I'll do is I'll pause the video here and wait for this to solve for all design points, and when that's done, I'll come back into the video. Now, disclaimer, sometimes when I pause it for long periods of time and I come back into it, it says I can't restart. So that means it could be another video. So if it is, so be it. I appreciate the patience, and looking forward to seeing some different results this time, and getting a little bit more insight before we eventually get into our grid independence study. Okay, see you in the next video. Thank you. Well, everybody, as expected, the video wasn't able to resume after the pause, and it cut me short. So fortunately I was able to stick this part of the video to the end of the last video and make one big video out of it as opposed to two separate ones. So just letting that in to give you a brief explanation of why you're potentially looking at a different background. Yeah, it's a good bit down the road now from the last video. Yeah, so having rerun this, we've finished these all again, and as expected as well, we still have a problem. We're still looking at a problem in there in around design point 4. So in around 3, 4, 5, we still, despite the changes that we made in the solver the last time, we still have the same sort of a scenario where our trends are taking us a certain way, and then when we start hitting these higher angles of attack, we get out of range values or out of trend values. Okay, they just don't follow the normal, not the normal, but the expected procedure. And in this case here, it is again at design point 4 apparently, where we have a very sudden spike in say the likes of the lift force. We have a very sudden spike there as well, obviously in the coefficient of the pressure coefficient. And we have a big drop here as well in our drag before it again scoots us back up in the following design point at an angle of attack of 6. So there's something funny happening here, and it's we now have more tools to get to the bottom of it, simply by virtue of the fact that I retained the data when I ran the calculations for design points 3, 4, and 5. So what we can do is pop into the solver and see what's happening at these design points. And my first place always will be at the contours, because we might see some indication of maybe certain drops in pressure at different locations, or reductions in velocities at other pressures where we normally shouldn't have. My indication before looking at this is, as I had mentioned a couple of times before, laminar separation bubbles, and maybe at design point 4, for that given angle of attack and the Reynolds number we're running at. It hasn't really been a separation bubble, it's just been a separation that hasn't reattached, and we've had some difficulties. So what I'm going to do is, I do reckon it's design point 4 here that's given the difficulty. It's definitely between some of these. Maybe it could be a case that design point 3 hasn't come up enough, but I can see with the likes of the lift force here and the lift coefficient, we could see a jump and then a reduction again. So there's kind of a hill there at design point 4. So what I'm going to do is I'm going to turn on design point 4 by setting that as the current. Okay, so that's now the current. I can set that as a current because I have retained the data, and all that means is now when I open up my solution or open up my solver, it'll open up the data that was saved, that was retained for that design point, as opposed to looking back at design point 0, which was the 0 angle of attack. So up to now, every time we've opened up the solver, we've kept opening up the design point 0 data, and now we have we can access the design points 3, 4, and 5 data, which are respectively angles of attack 4, 5, and 6. So there's our flow field again and our mesh. And what I'm going to do is I'm going to go on down to graphics here. I'm going to open up my contours, contour 1, showing a velocity magnitude. Let's get a look at that and see what this looks like. So we do have a laminar separation bubble here. It's a prolonged one. Doesn't look awful bad compared to what I might have thought it could have looked like. But we could see here the very noticeable bulge along here. That is obviously causing difficulties. You can see how the boundary layer, the wake, got very thick very fast here. And so it seems there that you can see that the blue region, the how far up the kind of the low speed region has gone, where we are, looking to accelerate flows over the front. The very leading edge here has a very high gradient of velocity coming over that. But then it dies off fairly quick with this particular airfoil, and there we are. I can see this wavy pattern, and I can actually see the mixing in there. So there's no, we're not turning on any paths just now or streamlines, but you can see it seems to be a slightly higher velocity in here, and we'll have the lower velocity coming out over the top. But yeah, it's obviously going to cause big trouble. That's not what we're looking to see. But I think what I'm going to do is I'm going to zip this in just to compare, because I have another 2 to look at. For some reason this trend hasn't followed through with the other angles of attack. I have an idea why that's happened, but we'll look at them first. Stick this one in here. Maybe just take a note that this is design point 4, which was the 5 alt 0176 degree angle of attack, and make that there slightly bigger. Bring it on up to 18. Okay, So that's that one. No harm, maybe just checking pressure as well, but we should know what to expect here. There's pressure. There's a big drop in pressure here, but the pressure is building up fairly quickly, again over the top of the airfoil. And then it's just not resolved enough to be able to see any sort of variations in that. Now we could look on that more. We could put in on path lines and see actually what's happening with the fluid flow in them regions. But again, we're meant to really only be looking at zero angles of attack here for this airfoil. This is just more a scratching of an itch, I suppose, more than anything. So that's that. I'm going to hit close, and then let's just check another one. All right, okay. Now, this one, make sure you do not hit use settings changes for current and future calculations. Use setting changes for currents. I'm going to hit don't save changes. The reason for this here is that we've just accessed the file and we've pulled up the contours for that and so on. If you click use the settings for the current and future calculations, you go back onto your parameter table, and they're all going to be lightning bolted again. You're going to have to run the whole lot again, which you don't want to do. So don't save your changes here when you're going through, when you're not changing anything, when you're only looking at contours. Okay, don't save them at all. So go over to this one, and then let's move back into design point 3, which is for the 4-degree angle of attack, which on a trend perspective appears to be the one that is still keeping in the general rate of change you might expect. So I'm going to set this one now to current. Go back into my solution and have a look at what's happening in here. So we'll look at, this is slightly flatter, more parallel to the flow angle of attack at 3 degrees. So hopefully we don't see that laminar separation bubble just as prominent in it. That will probably be there. It's obviously starting to separate, which takes in a good point when I say starting to separate. Don't forget that we're running this as a steady state analysis. The laminar separation bubbles and any of these external airflow problems, even at 50,000 Reynolds number, which isn't huge, there is transition regions in it. We should really be looking at this with the transient time step. So when it solves for a solution, every single time I solve this, every time I run a set of solutions for any of them design points, I will more than likely see different values. Now, they're not vary greatly at lower angles of attack, but at larger angles of attack, sure they will, because it just depends on when the solver has converged, whenever that particular phenomena is happening. But all types of phenomena are happening here. So sometimes we might have just got massively lucky, and it might have just looked like it was in range, depending on when it converged. But definitely that would be very lucky to hit on that, or maybe unlucky because you wouldn't have seen what actually has happened or got a good appreciation for what actually is happening. So back into the graphs, contours, contour 1, pressure should still be over velocity. I sure didn't save the changes. See save and display. Oh. So here we see this. We see a much more prominent wake or stream coming off the back of that, with a massive sort of separation back here. We've stayed attached. It looks a lot better. But what's happening now is that the airfoil, or the air moving over the airfoil, is scooting past a little bit too quick to give this time for the separation bubbles to come back. So have a look here, still stuck to the back of the airfoil. Now the other thing in this here is that we have a very pointy trailing edge here. Our aft point is a point which isn't great. If that was a rounded point, we might have had which we normally should have had, somewhat better of a grip here. But nevertheless, this is gripped. We're gonna have a big wake coming off the back here at this relatively shallow angle of attack. But that's very interesting to look at. And then when we look at our pressure distribution, what we might like to see here maybe is a significant change in pressure. We should see that in the contour as well. Let me scoot this over here and I'll take a look at this one. But again, we're very likely to see that exact scenario happen here. Even though it doesn't appear to happen there, it does. It's just whenever the solver had converged. So let's get this down here, and then this is design point number 3, which was for the 4% angle of attack. Auto 176, 4% angle of attack. I think I wrote that twice there. Just double check it. Nope, I didn't. Alright, so that's this one here. Now, let's try and see what the big angle of attack looks like. So let's just look at pressure here first. Pressure, display, and there you are. Look. So there we'll have a massive section here of a lower pressure. So it's generally low all over the place. We're low where we're expected to be low, and then a wee bit of a pressure build here in the middle, and then we get the low pressure again manifesting itself there. So yeah, it probably just wouldn't be the best looking of regimes, albeit it's still low pressure in the top of the wing for an angle of attack that's coming in from the bottom left. Yeah, but that's at this moment in time. Look at it a second later, it could look completely different. So again, transient flow would be the name of the game, or transient analysis would be the name of the game for these applications, clearly, especially at angles of attack. Okay, let's close that and let's exit this. Again, we want to exit yes, and remember, and do not save changes. Okay, and last but not least, I'm going to check the design point 5, which is 6-degree angle of attack. I'm not going to run this in a transient state, by the way. I will do a transient analysis when we do 3D. So I'll show you how to do that. But it's just we're going too far off topic here already. Set this one here as current, design point 5. Back in the project and open up solution again. Incidentally, when we run the 3D analysis, that'll give us results that would be better compared, not better, because they mightn't be more like the published results of Microselic or Winslow or any of the other contributors, but the results we get out of the 3D analysis would be more indicative of what we would want to compare against, obviously, the results of the experiments that were carried out, more so than doing a 2D analysis, which we have an awful lot of idealizations in this here as well. So the 6 degrees, going to graphic contours, contour 1 should be at velocity. And there's another big coming off of that. Oh yeah, look at that one. There is more characteristic laminar separation bubbles, and look how far upstream they're occurring now at 6-degree angles of attack. So what's happening here now clearly is we're only at 50,000 of a Reynolds number, and the big angle of attack isn't just working with it. The big massive separation here at the back. The drag is absolutely huge on it. And you're probably starting to get into stall characteristics here because there's not enough energy in the free stream to keep the air that's rolling over the airfoil here energized adequately. And at the bigger angle of attack, this is what we're getting here. I didn't check design point 2 to retain the data when we were looking at that, but we probably, well, again, it depends on the time that the solver finished and it was satisfied that everything was converged. But we could see maybe from angles of attack, certainly of 3 degrees, 4 degrees, 5 degrees, well, 4, 5, and 6 definitely, laminar separation bubbles are there. And if this study was not looking into STEM racing competition car front wings, yeah, there's some very interesting work to be done here. Could even be a paper on it, just saying. But yeah, there is 6 degrees on that. Yeah, I'll say that way at 6 degrees.
It's absolutely phenomenal stuff. It's brilliant, absolutely brilliant to be able to see these results. And then let's put it into here and just actually should have did was put 4, 5, and 6 in order, but it not really matter. Mark me there, like 4 looks not as bad as 6, but it looks better than 5. 5 actually looks the best there. But as we all know, that's just by pure chance that it was captured at when it was like that. It wasn't caught red-handed as such. So let's go to design point 5 and let's make that 6 degrees. Yeah, so we can see. Aye. But yeah, that's brilliant to see. Not brilliant to see. Nobody likes that, but it's a nice piece of results off of airfoil performance, given Reynolds numbers and angles of attack that you see, and a huge amounts of studying done on airfoils, not so much on the NACA 0009 that I have seen, but definitely the 0012 for the laminar separation bubbles at certain Reynolds numbers, and it is at these low speed Reynolds numbers where the kinetic energy in the airflow, the free stream, the airfoil, it can't keep up with the airfoil as such, if you like. So yeah, there you are. When we look at the pressure distributions, yeah, there's no real continuity between 3 coming on to 4 coming on to 5, and that. If anyone say, well, what angle of attack do you want to run your airfoil at? I'd say here, let's go 5 degrees at this. But if we waited, as I said, a split second later, we probably would have seen this bubble, would have propagated, not propagated down, but maybe would have developed an awful lot more into something we're seeing here. This region here is obviously lifting. And it's obviously lifted at a very early stage because we see it there. It's just come back down again and maybe reattached at that section. But yeah, so that's it. What's the answer to this? We went through all this hassle again, made this other video to go in and make the changes. Well, at least we ruled something out. At least we ruled out there that this wasn't, when we were looking at our table of parameters here, that it wasn't to do with convergence. It wasn't to do with definitely, well, it wouldn't have anything to do with the solver as such. We could see the 4 equation is probably the best method to use there, because we clearly have turbulence occurring at these higher angles of attack anyway, and the transition equations are appropriate. And as well as that, 2D well-defined mesh, structured mesh, there's very much little else we could do with the spatial discretization or the pressure velocity coupling. So yeah, it's probably down to the fact that this is being done on a steady analysis, where transient analysis would have delivered much more reliable and definitely much more stable results. Okay, so remarkably in instability, within flow comes, stability in results, providing you're on the right solver. But again, we're not going to do that for 2D. Next step, next video, 100% is definitely going to be the mesh independent study, the grid convergence index method for mesh independence. So yeah, hopefully you've got a little bit out of this, and you found it worthwhile. So if you did, I'm glad, and I hope it helped you, and I'm happy there from my own perspective as well, that I ruled out anything that might have went wrong with the setup. I don't want to put anybody wrong myself. So with that, thanks very much, and I'll see you in the next video for mesh independence. Good luck.